And what the Chinese remainder theorem says is that this has a unique solution. Mod PQ. So obviously, if you have multiples of PQ, you can get more solutions to this, but if you restrict yourself to mod PQ, then we can always solve this. And what's really interesting is that if our n from Zn is a product of two primes, then that means that there exists unique x1 and x2, which works slightly differently. Such that x is equal to x1 p to p prime here. So we can find unique x1 and x2 such that this is true, and we can actually do the opposite. We can go from, if we have some x in Zn, we can go to a value in P and a value in Q just by taking modulo P and Q. Very, very straightforward. And what that means is that we can go from, in general, if n is some prime power, this is, I'm skipping ahead in my slide a little bit. Yeah, let me skip ahead. And then I'll show you a simpler example. If n is some product of primes, something like that, and Zn is isomorphic to this means that we can work in Zn, this is Zn star, or we can work in the primed component-wise and then recombine using Chinese remainder theorem. We have the option to work in whichever one of these we want to and then recombine. Provided, of course, that we know factorization of n. That's a really critical thing. If we don't know the factorization of n, then we have to factor n first, and then we can move back and forth. But that's what Chinese remainder theorem tells us, is that the two are equivalent. You can work in a set of primes, the factorization space, or you can work in Zn. And this is really helpful because oftentimes there's ways that we can work in Zp or Zq, things that we can reason about modulo prime that are difficult to reason about when you're modulo a composite number. To give you a quick example, we take n to be 187, which just happens to be 11 times 17. And let's say we wanted to find out what is 42 times 111. So we say call this one X, call this one Y, and we can say X1 is equal to 9, or 11. This way, X2, 8, 17. So you can check if you're following along with your calculator. Just take 42 mod 11, you should get 9. If I haven't screwed this up, take 42 mod 17, you should get 8. And we'll do the same thing with Y. And what we should get is 1 mod 11 and 17. And what we end up with is, we just multiply 1 by 9, 11, and call this Z, and this ends up being 4 mod 17. Again, feel free to check my math here. And then in polynomial time, we can actually use CRT to solve this. Or if you have pre-calculated what P prime and Q prime are, you can get this fairly quickly. So I happen to have those already, but you end up with that. So I'll leave it to you to look up the actual CRT algorithm. It's relatively straightforward. It's just more mechanical than I want to go through in this class, since the goal of this class is not to go through discrete mathematics, but simply show you how it can be used. I'll leave it as an exercise to go through, as hopefully you have seen this at some point in your mathematical career. But the point of the exercise is that we can take any composite number. If we want to work modulo that composite number, we can work in the prime powers and then use CRT to recombine. That's the point of the exercise here.
Sorry, can we further decompose the, for example, the P1 to the power of alpha 1? Is it possible to split into 2 the extension field where the exponent adds to alpha 1?
Sure, that's a good question. I'm not sure that you can, because I don't know that the two are independent at that point. So I don't think I think you lose the uniqueness property. So it depends, I think, on what you're doing. You'll lose uniqueness, which may or may not be a problem, depending on what you're trying to do.
Okay.
Yeah, if you think about it, let's say that Zn is like 7 times 7 times 19. Then you could swap those two elements.
Right.
And you don't have unique elements anymore.
In general, yeah, I don't think like Z4 is equal to Z2 times Z2. At least not under the usual Cartesian product. But
Yeah.
maybe with some other more sophisticated notion of product, it could be done.
Yeah. All right. So let's ask a different important question. What is the size or order of Zn star for arbitrary n? Does anyone know the answer to this one? So let's go back to our definition. What are the elements in Zn star? What's the requirement here?
All numbers co-prime with n.
Yes. So, really, less than n so we call this x, n. And this is the definition of phi of n, aka don't worry too much about the name of it. It's just a interesting, well, not even interesting, just a trivia of historical artifacts. Phi of n, if you keep this definition in mind, a lot of other things will make sense. Phi of n is the number of numbers less than n co-prime with n. And for convenience, we also say that phi of 1 is it's just a convenient thing we do for ourselves. So, let's see some examples of that. What is phi of a prime number? By the way, this is just my way of writing phi. You probably see other people write it this way. The reason I write it this way is because sometimes people start writing it that way, and to me that looks really confusing. And because my handwriting on the board is not the greatest, I write it that way so that it's pretty clear what that symbol is. Once you've seen it once you understand once that that's. So let's see, p is a prime. Always a prime in this class. How many numbers are there less than p? Co-prime with p.
Minus 1.
P minus 1. All right. Let's say now give you some power of a prime. What's the value of p? How many numbers less than p to the k are there co-prime with p to the k? This one's a little bit trickier.
I think that's not a multiple of p.
Yeah. Has to not be a multiple of p. And so you end up with p minus 1 for that first set, and then do that k minus 1 times p raised to the k minus 1 times over and over again. So you're just basically taking out that one value, and then you do that p to the k minus 1 times. You just sort of walk it over and over again. I'll let you work through that a little bit more. So that leads us to if n, as we had over here, 1 dot L. Okay. Yeah. So basically by the Chinese remainder theorem, this works out such that basically going to do this for each of these. Everybody see that? Chinese remainder theorem allows us to break this down into components by each of the primes, which you can recombine using the Chinese remainder theorem, and therefore you have size this times this times this times this And so one minus one. So if you know the factorization of n, then you can figure out the size of Zn star. And if you don't, then, well, you're a little stuck. As we'll see again and again, this will come up. But don't worry too much about memorizing this formula. We're not really going to ask you, what is Euler's quotient of some random number. But I want you to get used to this idea, first off, that the order of a prime field is 1 less than the value of the prime. The prime, this p to the k minus 1 thing, it's not something that's going to come up very often, but it is true in general, so I showed you for completeness. And the idea that if you're working in prime powers and you just multiply those together. Almost always what we are going to be dealing with is going to be something a little more straightforward, like this. This is what you're going to see a lot. So you should understand this, but don't memorize it. Don't worry about, you have to know it. You don't have to memorize this one. Understand it, though. Understand where it comes from. And this is what you will see over and over again. I don't think you'll need to memorize it because you're just going to see it so often that it'll become very much ingrained. And so that's how Zn works. If you use to a Zp star, then Zn, especially if it's a product of two primes, lets you work this way. Questions about Chinese-Remainder theorem and working in Zn star? This is going to be the basis of our study, which is really cool because we're going to use number theory to construct something that hasn't been broken in at least not broken directly. Quantum computers may break it, but only by basically circumventing classical computations. All right. Let's get to, I'm sort of working right to left here, which feels a little bit backwards, but. So, let's say we're working in Zn, and let's say that A is some value in Zn. What happens if I do this? So I take some value in Zn, and I raise it to the power phi of n. And what do we say phi of n is? What is phi of n?
The order of the group Zn star.
It is, and that's what we need to know for this. But remember to always go back to this definition. It's the number of numbers less than n that are co-prime with n. So it is the order of this group. So what do we expect if we raise something to the size of the order of the group? What should we get back? This should always wrap around and will give us identity. So that's the easy way to think about this. And I've actually just, after going through all of my notes for this class, I realized that my knowledge of group theory was a little bit incomplete. I actually went through and pull together some references for group theory and put together a whole set of notes on everything, not everything, but a large group of things that you can prove with group theory that doesn't require any knowledge of Z and ZP, what the structure of the actual group is. And this is one of them. That you take anything in a group, raise it to the order of the group, you get back ahead. So that's the way to think of this, not as some crazy numbers in Zn thing, but if you're working in a group and you raise something to the order of the group, you'll always get back together, or identity, if you will. All right. If we are working in a prime field, so now we are looking at mod P, where P is prime. And why am I raising to P minus 1 here? Anybody see what the relationship is to the previous question?
It's just the same.
Yeah.
By definition.
So phi of P is P minus 1. What should we get here? Identity. And this is Fermat's little theorem. Don't worry too much about the names. We're not going to be on the exam going, tell me about Fermat's little theorem and its significance. No. Just to give you context. And again, these you can prove for cyclic groups in general without making any assumptions about the underlying group. All right. I'm going to erase my example. And start over. So let's say that you have some generator. So Z and star happens to have a generator. We're going to call it G. And I ask you to do something like G to the A mod set N. That's as to how long, like how complex is that to do on a computer? Let's say N is really, really big and G is also some really big number. Some 1024, 2048 bits, a big number. What kind of complexity are we talking about to do a modular exponentiation?
Polylog of n.
Yeah, it's something, it's actually polynomial time, not even polylog. So this is poly time. And if I ask you to then take that and do that. Polynomial time by composition. But could you simplify that? If you knew that I was going to ask you to do G to the A and then raise that to the B. Can you simplify this a little bit? Starting with G. This is what am I talking about? So you notice from what we said over here with Euler's theorem, this is actually what you had. Right? So if you knew A and B and you wanted to compute this, you could take AB, just do standard multiplication with them, mod phi of n, and then do the modular exponentiation. What if I asked, like, I gave you these two values, and I wanted to do that. You could do this directly, and just like compute everything step by step. Or sorry, that's not true. Try to get that. And again, you'll notice that this is mod 10. What does that suggest? We're always working with this generator. And we know what phi of n is. It's a big assumption to make. But assume we have phi of n for the moment. This suggests that there is an isomorphism. Sort of like what Chinese remainder theorem told us about working with Zn. There's an isomorphism between star and Z plus, but it's not n, phi of n. Very important. The order of your group, whatever that group happens to be. I have my notes here. So yeah. K is equivalent to a mod n, and everything else that I pointed out there. So this really helps. Anytime you're thinking of things Zn or Zp star or whatever it is, realize that you can basically map everything to just addition and multiplication. Really helps you simplify things. So remember this as you're working with, it's actually, you can substitute any group here. And this is the order of your group. And if you have a generator and you know the order of your group, you can do this. If you don't have a generator or you don't know the order of the group, you can't. So that will be critical. But if you know the order of your group and you have a generator, just working things, Z, order of your group, and addition. Much easier. So much easier. Questions about that and Euler's theorem, Fermat's little theorem, and so on?
Yeah, let's check. For this isomorphism, does it only work if the group is finite, or does it also work for countably infinite? Assuming it's just a
I'm
generator.
pretty certain it still works for countably infinite groups.
What does group order mean for
As long as it's infinite, I mean, as long as you have integer number of things, you can still generate it in principle.
Yeah.
But then what's the order? What does the order mean then?
I don't know what it would mean to generate a countably infinite. I guess it could still work.
Yes, yeah, you take
so-
an element G, then you raise it to enough. You take the set of G to
Yeah.
the Z, overall integer
I
set.
think
If that
it
is
still
true,
works.
No, I'm asking what's the phi of n? What's the order of that group?
I guess if it takes infinite elements, then it would be infinity, but you can still define isomorphism
I
between
think you
groups.
still
independent.
could. Not sure if it's as helpful.
Yeah.
Because the reason we use a lot of these modular groups is that it gives us a fixed size, fixed bit size, and allows us to reason with the security of those sizes of those groups. Whereas if it's countably infinite, I mean, the natural numbers are countably infinite. So working over, the order here is now countably infinite, and we just have addition and
You do get a
multiplication.
structure transfer then.
So it still works.
Yes, I
don't know how subgroups would work in that case. What would it mean to have a subgroup of a countably infinite group?
probably wouldn't. It might. I don't know if it might just end up being isomorphic to Z or something, but I haven't.
Yeah, I think it
haven't
might be
thought
just
about this.
isomorphic to Z. So yeah. Okay, let's talk about quadratic residues because that's also going to be important in another lecture. I'm going to erase Euler's theorem and Fermat's theorem. Quotient for now, and let's start over here. And let's talk about quadratic residues. I think this was briefly mentioned, if not here, then in class. Does anybody have a notion as to what a quadratic residue is?
A number that can be written as a square? Or is it a
Yes.
group number that can
Yes, exactly. That's it, exactly. So, how do I write this in my notes? So, if you're given some h in, we're going to work in ZP star for now. As mentioned previously, if this works in ZP star, we can bring it over to Zn star. Does there exist some g such that h is equal to, they use 3 different letters here. That was not brilliant of me. G squared mod b. Exactly. Exactly as was said. So, if I then take h, instead of figuring it to, maybe I shouldn't have erased for myself, but it must be a memory test for you. Instead of raising it to P1, I put it to P1 over 2. What should I get? Hint, what happens if I substitute G in here? What happens here? It was right on the board just a moment ago. What did we get out of it?
1.
Okay. Yeah, get 1. Get that, get the element. So, and yeah, the reverse is also true. What follows from this, we can use so many different, too many different pieces here. What we get is, so first off, what's the order of our group again? ZP star, we have P minus 1, right? And if P is prime, and assuming it's an odd prime, i.e. it's not 2, P minus 1 is even or odd. It's even. It's going to be even, it's going to be a composite number. So, what that means is that exactly half all of the elements in ZP star are quadratic residues. G is equal to square root of h. Then I'll use t instead of whatever. You get the idea. All right. Not a ton of time. So I'll run through this fairly quickly. I want to get to another piece that's a little more interesting. how do we find? I'm going to change symbols here. T is equal to some square root of h mod. So if I just ask for square root of 1 mod p, what should I get? Square root of 1 in general is?
Plus or minus.
So, and what did we say? Plus 1 is equal to t to the p minus 1. Combine those two, and we say plus or minus 1 would be equal to t minus 1. Splitting that out, we get this is just a lot of algebraic manipulations. I'll let you work through this at some point. Basically, you just mess around with the algebra to see that you can take h p plus 1 over 4 if that exists. P plus 1, this must be an integer. So that restricts what we can work with. But and again, by that isomorphism, we take this p plus 1 over 4, figure out what that is for p, make sure that that's actually an integer. And you can very easily take a square root in any p for which this is true. So oftentimes that means that we'll have p is equal to 3 mod 4. Don't worry about this too much. We're not going to be testing you on can you find square roots mod p or something like that. Just the point is it's pretty quick and easy to take a square root of 1. It's a relatively easy thing to do. What about other roots? A little low on space here. Let's do this. H is equal to g to the e mod p for some given e. Can we find g? Well, if g is coprime or relatively prime with p minus 1, aka phi of p, then we can just say again, I'll let you work through this and say that this is where that isomorphism comes in really handy. It's basically h to the d. I apologize for being right at the bottom of the board here. It's g to the ed, which but that only works if E is coprime with phi of. And this is going to be the basis of our exam. if you know factorization, you can do all of this stuff. If you do not, then you must factor a very large term. Right, that's something we will go through in class. Questions about quadratic residues so far? I'm going to try in just a few minutes to go through a bit of notation that's going to be really helpful for you to know in class. So a lot of this is sort of abstract math that by itself is interesting if you're interested in math, but it'll really come alive when I get a chance to go through RSA and some of the crypto systems that use this. I apologize that this is all seeming like random bits of mathematical background. Let's talk about symbol. So this is just a bit of notation, but it's going to make it a lot easier to reason about things when you work with it. And what it is just A over some prime P going to be 1 if a quadratic residue -1 if not quadratic residue. This is not standard notation, by the way. This is just I'm writing here on the board. 0 if A 0. So Lausanne came up with this long after I think Euler figured out the social function and everything else in terms of quadratic residues, and maybe it's Gauss. I can't remember. But Lausanne figured this out long after we understood quadratic residues. But he said, hey, what if we write things this way? And it turns out this way of writing things is super helpful. The original definition was actually something like this, which, as you've seen before, works out very easily. So this is your super quick and easy way to check if A is a quadratic residue. And it has some really handy properties. Because things like AB is A over. Basically, if you have some number that's multiplied AB, yeah. Similarly, try to end with this. Don't know if I will have a chance to give you the example I was looking for, but we'll just introduce this quickly. Think about why it's useful, and I'll leave you with some parting thoughts to consider before the next lecture or two. Have the symbol. And it's just a generalization of Legendre. We're going to take n, again being our set of prime powers. So before, Legendre was actually only defined for prime numbers in the denominator with lower half. Here it's defined for composite numbers, and it's defined as being that is if one, otherwise Sort of like over here. Except here, if A is divisible by any factor of n, then we say the Jacobi symbol becomes 0, which makes sense because then one of these would be 0 as well. So it's still fairly consistent. And it has some very nice properties, very similar to over here. And interestingly, we can also do this. Have a composite in the bottom half. That. And we can evaluate this. A logarithm, basically time and the size of the bit size of each of these. So an important question, if the Jacobi symbol of A on n is 1, is a quadratic residue. I have a great example where I go through that. But I want you to think about if this is your breakdown of your Jacobi symbol, could you get a 1 here, but have some number that's actually not a quadratic residue whatsoever? So yeah, so this is your to consider section, i.e. optional homework. So here's your first question. Second question is that P star what are the implications to cryptography if I give you some ZP group such that this prime P is 2Q plus 1 for some other prime Q? What does that mean? Right, just think about some of the subgroups of that. What does that produce in terms of groups that we can use? And what does it mean in terms of structure of those groups? What does it mean in terms of quadratic residues, etc.? And if you need to, you can assume that P is 3 mod 4 as well. You can add additional support. So think about that. This will probably come up. So give that some thought as we just run. So questions on any of this before we wrap? I'll stick around for a few minutes if you have any questions about this or any of the other elements from class. And thank you very much.